Okay, let's get started. Okay. So, before starting today's class, uh, I believe many students will register to this course. I'm sorry. So many students registered to this course during the registration change period. How can I say? The 수강 점검 기간. So I will briefly introduce about the this course. So which means that I will introduce about the Piazza platform. Then also uh, I will introduce about the self-attendance check system of this course. So I believe the number of students enrolled in this course is equivalent to the maximum capacity of this classroom, right? Maybe. So I believe 7 students have registered this course. But I can find some available seats here. I believe some students are late for this today's class because this course is the morning class. So, so actually, I will show the. So this is the resource tab of the Piazza. Piazza is the class management system platform. So as you can see, you can find the lecture note here, and then also you can find lecture video link in this table. So as I promised, I recorded this lecture using Zoom, and then I post the recorded lecture video on YouTube, and then also you can find the list of the lecture video links in the resource tab of the Piazza. Okay, so if you missed some classes, then you can watch the recorded YouTube video. But usually, I encode the recorded video on during the weekend or on Friday, so it will be posted sometime later. So if you missed some classes, then you can watch the YouTube videos. Also, and then in order to access this Piazza platform, then you need to register Piazza. Okay, so this course. So you need to sign up the Piazza using this access code. Okay. And I found about 45 students registered the Piazza. So we have so which means that some students did not register Piazza. So I recommend to register the Piazza platform because I will post the lecture videos or the lecture notes. I post the lecture note on the Blackboard, but I will post the lecture video link only on Piazza. Okay. Also, do not forget checking the self-attendance link on the Blackboard. So we use the self-attendance check system. So I will not call your names because I think it's the waste of time. So you need to check your attendance by yourself on Blackboard. 문제가 아닌데. I cannot resolve the Blackboard issue, unfortunately. 안 돼요? 지금? 체크. 지금 안 돼요? 체크가? 액세스가 안 돼요? 아, 그래요? 오케이. So this, I believe this is the start of the semester, so I believe many students are accessing the Blackboard, so that's why the Blackboard system is so slow. But try to check. Okay, so actually, I will check your attendance since the next class, the Wednesday class. Okay, so Okay. Do not forget checking your attendance on Blackboard. So this is what I want to say before the regular class of this course, because we have many newly registered students. Okay. Okay. In the previous class, we learned about the number systems of this system. So I said, so actually the real signals in our real world is the analog signals, but in order to process these analog signals using the systems, analog signals need to be converted into the digital signals. And then, as you know, the digital signals have only two levels, 0 and 1. So digital systems actually use the binary number systems. So in the binary number systems, each digit of a binary number system has only also two levels, 0 and 1. That's why digital systems use binary number systems. Okay, and then I believe you already learned about this binary number system during the middle school, high school, right? Maybe middle school. So each digit, actually in the number systems, each digit represents the power of base number. So because the binary number system uses the base 2 number system, so each digit represents the power of 2. So using this property of the binary number system, we can easily convert the decimal number to the binary number or binary number to the decimal number, right? So it's not difficult. Also, these are powers of 2. So if you can memorize the powers of 2, then it will be convenient for you, because it's the systems frequently use these numbers. Okay. Also, okay. And then we also frequently use hexadecimal number system, because if we use the binary number system, so each digit have only two values. So the length of the number is very long. So we use the hexadecimal number system in order to use the compressed. So if we use the hexadecimal compressed this binary number system, so actually the 4 digits of binary number system can be compressed into the 1 digit of hexadecimal number. Okay. Okay. So we also learned about the large powers of 2. So in the binary number system, kilo means 2 to the power of 10, right? It's the the 2 to the power of 10 is the 1024. Actually, in the decimal number system, kilo means 1000, 2 to the 10 to the power of 3. But in the binary number system, kilo means 2 to the power of 10, 2 to the 10. So it is because, as I said, 1024 is the magnitude of 1024 is similar to the 1000. It means kilo in decimal number system. Also, we frequently use mega. Mega means the 2 to the power of 20, right? And then giga and tera. So we frequently mention that the size of our computer system is 4 gigabytes. So in this convention, the giga means is 1, 2 to the power of 30. So 4 gigabyte means 4 multiplied by 2 to the power of 3 byte. Okay, 4 gigabyte, very large number, but we can use this number like this. Okay. Okay, so So we learned about the arithmetic of the binary number system. But you know, the arithmetic of binary number system is also the same to the arithmetic operations of a decimal number system, right? So add is add, subtract is subtract, then multiply is multiplying, and then and so on. Okay. So let's review the binary addition. So how can we calculate the 1001 plus 0101? So as I mentioned in the previous class, we can start from the RSB of the binary number. So what is the RSB? RSB is the rightmost digit of the number. Okay, the binary number. The RSB means the least significant bit. Okay, so we can start from the RSB of the binary number, right? So it's 0, so because the 1 plus 1 equal 1, 0. So carry is generated, so carry is propagated to the next digit of the binary number, right? So for this digit, so we need to perform 1 plus 0 plus 0, right? So it is 1, it's simple, and then the carry is not generated, so carry is 0. So 0 plus 0 plus 1, 1, and so 1. So we can easily calculate the binary addition. Yes. Then how about this example? It's the 1, 0, 1, 0, 1, 0, 1. So why did I show these examples? So what is different? This one and this one. What is different? So what is the difference is that in this operation, if we use only 4-bit binary number system, so 4-bit binary number, then the result is correct. Okay. But how about this? We also perform the same 4-bit binary number plus 4-bit binary number. Then how about the result of this operation? So the result has also 4 bits, but this result is incorrect. It's wrong. Why? The carry is generated at the MSB. Okay, most significant bit of the binary number. The carry is generated. So actually, the correct answer is the 10001. So which means that if we use the 5 bits, the result number, then we can generate the correct answer for this operation. But why did I show this example? So this is the answer for this operation. So this is the 9 plus 5 is 14. The correct answer for this is the what's this one? This is 6, and then this is 8, 11. So this is the 17. But it's incorrect answer. So you may think that in the normal arithmetic operation of the decimal number system, then we can easily calculate like this. So 11 plus 6 equals 17. Also, 4 plus 7 equals 11. So which means that we can, if we increase the value of the result number, then we can generate the correct answer. But why did I mention this one? So in the binary number system, it's also the same. Which means that if we use the 5-bit and the result number, then we can generate the correct answer. But in this case, we assume that the result has also 4 bits. So if we use the 4-bit result number, then this result is incorrect in the digital number system. So why did I mention digital system? So you need so in the software, so which means in the actually in the real world and in the mathematics and also in the software, we easily think that our resources are infinite. So for example, if we just add the large numbers like the very large number plus very large number, then it will generate the correct very large number in our brain or in our real world. But we are learning about the hardware, so you need to think that hardware system has limited resources. Okay, so these the systems operate on a fixed number of bits. Okay, so which means that we are using these 4-bit numbers as an operand, and so also we are using another number as an operand. So 4-bit, the 4-bit operand, and then we set the number of bits in the result is also 4-bit. So which means in a digital system, we just implement the result number using 4 bits of hardware resources. Okay, so if we just use the 4 bits of hardware resources, then we cannot represent this large number 10001 because this number is 5-bit number. Okay, so this is very important. This is the system or hardware. Hardware has limited resources. Okay, this is very important. That's why if we use the 4-bit number systems in a hardware, this hardware cannot generate the correct answer if we use the large operands, like 13 plus 11 plus 6, right? The very large number. So this result, actually this situation is called an overflow. Okay. So the meaning of overflow is that when a result is too big in the available number of bits. Okay. So in this example, the result has only 4 bits, but we cannot represent the 17 using the 4-bit of the binary number. So this situation is called an overflow. Okay. And then actually a computer hardware misdetect overflows. Okay. So for example, let's think about the C code, like int A and B. So this is C code. And then I mentioned that usually the integer an integer has 4 bytes of size, so which means it's 32 bits. But if we assign very large number in A and also the very large number in B, and then if we just perform the A plus B, and then it will also generate the C. But the C can be also very large. If the result of C cannot be represented using 32 bits of binary number, then this is an overflow. Okay. So if overflow is detected by hardware system, then hardware reports this overflow error to the software. But if not, then hardware just generate the incorrect answer, incorrect result. So you may think, oh, it's just incorrect, but it's very critical in the system, right? Because our software or our system generates the incorrect result, then it will operate incorrectly, then it will generate the unexpectable answers or unexpectable result. So it can also generate the disaster if the system is very critical in real world. Okay, so you need to remember that if the system operates on a fixed number of bits, it means the system has limited resources, so you need to detect the overflow. Okay, so you need to know about the overflow. Okay, and then let's think about the signed number, signed binary number. So what is a signed number? In the real number system, the plus a or minus a. So we call this number is the signed number system. So how can we represent a sign of a number? It's simple, right? So if we use a signed number system, a sign has only two values, plus and minus, right? The sign has only two values, so which means that using a binary number, and binary number has only two labels, like 0 and 1. So actually, a sign of a number can be easily represented using a binary number system, because a sign has only two values. Each digit of a binary number has also only have two values. So we can represent plus a sign of a number using 0 of a binary digit, and minus a sign can be represented using 1 of a binary digit. Okay? It's simple. Then how can we represent the signed number using a binary number system? Actually, there are many cases, many available cases, but in this class, we will learn about the two different cases of the signed binary numbers. The first case is the sign and magnitude number system, and then the second one is the whose complement number system. Okay, let's think about the sign and magnitude number system. Actually, this number system is very similar to the signed number of a decimal number system, right? Like this. So what is the minus number of plus 2? It's minus 2, right? So in the decimal number system, we frequently use this number system. So actually, this number represents the magnitude of number, and then we just add the sign in front of a magnitude of a number. So we can easily represent the minus number using a sign of a decimal number system. So in the same way, we can also represent the minus number in the sign and magnitude number. So for example, this is 100. This number is 4 in decimal number. And then if we just add 0 in front of this number, so I said that 0 means plus, okay, in the binary number, then we can say, oh, this is the plus 4. Also, in the same way, if we just add 1, then and the 1 and 100, then we can say, oh, the MSB of this number is a sign of a number. So, oh, this is the minus, and then this is 4. It's a minus 4. So we can represent the signed binary number like this, the sign and magnitude number system. So in the sign and magnitude number system, the MSB of a number represents a sign of a number, and then the remaining bits represent the magnitude of a number. Okay, this is the sign and magnitude number system. So we can represent this A like this. So just if A is represented, A is composed of n bits of this small n minus 1, n minus 2, and so on, then A represents this is the sign bit, the MSB of this A is the sign, and then the remaining bits are just magnitude of a number. So this is the example. We can represent the plus 6 like the 0, 1, 1, 0, and then minus 6 is the 1, 1, 1, 1, 0. So MSB represents just the sign bit, then these are magnitude. So as also we can know the range. So what is the largest plus number using the sign and magnitude? So if the number is represented using n bit of a binary number, then what is the largest plus number? The largest plus number is the 0, 1, 1, 1, 1, or ones. So this is the largest plus number of the sign and magnitude number system. Then what is the largest minus number? The largest or smallest represents the magnitude of a number. So the largest minus number is the 1, 1, 1, 1, 1, 1, 1. So this is this one. Okay. So as I mentioned, we can easily represent the sign bit, the sign of a binary number using sign and magnitude number system. Then this method is similar to our real method that represents the minus number. Okay, it's actually in the real world we use the sign and magnitude number system in the decimal number system. But what is the problem? So this example shows the minus 6 plus 6. Okay, so this means the minus 6 plus 6. So we know the result is a 0. Then how about the sign and magnitude binary number system? So we can calculate so this is the minus 6 and this is the plus 6. And we can just perform AND. So actually, in a sign and magnitude number system, MSB of a number represents the sign of a number. So this is actually this bit is it has the different meaning. It's a sign bit. But if we just perform the addition using the adder of the hardware, then it generates the result like this. Okay, so it's a 0, and then it's a 1, and 1, then 1, 0, 1, 0, 0. Okay, it's not 0. Okay, 0, 0, 0, 0. So you may think that, oh, this is obvious because the MSB of the sign and magnitude number represents the different meaning. It's just sign. But we can, so in a binary number system, sign bit or sign is also represented using bit, the digit binary digit. So we want use the same adder hardware for performing addition of the sign and magnitude number system. But if we just apply normal adder to the sign and magnitude number system, and this number will generate the wrong answer. Okay. The another problem is there are two representations of 0, like +0 and -0. And you may think that, oh, in the real number system, like the decimal number system, we have only two zeros, two representations of 0, right? The +0 +0 and -0. Okay. So in the sign and magnitude number system, actually 0 can be represented as 1 0 0 0 because this is the -0 and this is the +0. So what's the problem? So we already know that, oh, this number is the same number, but in the hardware, these bits are different each other. Actually, if we just compare this number and this number, then we can know that, oh, this bit is just different. And we can say, oh, this is not the same number if we use the conventional comparator in the hardware system. Okay. So this is another problem of sign and magnitude number system. So instead of sign and magnitude number system, we use the COSE complement number system. Okay. So let's learn about the COSE complement number system. Actually, COSE complement number system has a single representation of 0. So this is the method that generates the COSE complement number system. Okay. So what is different? So this is the sign and magnitude number system. This one. And then this is the COSE complement number system. So what is the difference? This one. Okay. So actually, this part is the same. The summation of the remaining bit is just AI multiplied by power of 2. But actually, in the sign and magnitude number system, oh, where is it? This sign, the sign bit is just multiplied with the magnitude of the remaining bit. Okay. But in the COSE complement number system, the MSB is just represent the -2 to the power of n-1, and then this MSB bit is just added to the magnitude of remaining bit. This is the definition of COSE complement number system. So just compare. So you need to figure out the difference between the sign and magnitude and the COSE complement number system. So the sign and magnitude, the sign bit is just multiplied with the magnitude of the remaining bits. But the COSE complement number system, sign bit also has a magnitude of -2 to the power of n-1. Actually, 2 to the power of n-1. Okay, and then this minus number is added to the magnitude of the remaining bit. So actually, in the COSE complement number system, MSB represents the minus sign, which means that if we just check the MSB of COSE complement number system, and we can know that, oh, if this bit MSB is 1, oh, this number is the minus number. And then if the MSB is 0, and then this number is plus number. If the number is a plus number, but the MSB has a different meaning. MSB has also magnitude like 2 to the n minus 1 and minus. Okay. So then what is the largest positive number using the COVID number system? So we know this MSB represents the minus 2 to the 3. Okay. So if we use the 2's complement sign number system, MSB represents the minus 2 to the power of 3 and minus 1. Okay. So just you need to remember this, it's very important. And then the remaining bit is the same. So this is the 2 to the 2, and this is the 2 to the 1, this is the 2 to the 0. Then what is the largest positive number? Largest plus number. So because this is the minus 2 to the power of 3, if this number is 0, then if the remaining bits are all ones, then this is the largest positive number, right? So it's the 0, 1, 1, 1. So actually it's 7. Actually, the largest positive number of a 2's complement number system is the same to the sign and magnitude number system. The largest plus of the sign and magnitude number system. This is different. So what is the largest? Minus number, the most negative number. So in the 2's complement number system, MSB represents the minus number, very large minus number, right? It's a minus 2 to the power of 3. And then remaining bits represent plus number, plus magnitude. So the largest minus number is the just 1, 0, 0, 0, each minus 8. Okay, that is the 2's complement number system. So the range of the 2's complement number system is minus 2 to the power of n minus 1 to the 2 to the n minus 1 minus 1. This part is different. In the sign and magnitude number system, the range was minus 1 in the most negative number. But in the 2's complement number system, the largest negative number is equivalent to the minus 2 to the power of n minus 1. So at the 1, the MSB is 1, and then all zeros. That is the largest negative number. Okay. So this is just a definition. So just to remember the definition. In the 2's complement number system, the MSB represents the minus 2 to the n minus 1, the 2's complement number system. But in the sign and magnitude number system, MSB just to represent the minus sign. Okay, just to remember this. Okay. Then, so you may think that, oh, if we use the sign and magnitude number system, it's the same to our real number system actually. So it can be very convenient. Then, why do we need to use 2's complement number system? So I mentioned that in the real digital number system, we use 2's complement number system. Why? Because with the 2's complement number system, then actually the sign and magnitude number system has this problem. Like we cannot use the normal adder for the sign and magnitude number system. Also, there are two different representations of 0. These are the problems of sign and magnitude number system. But if we use the first complement numbers, and these issues are resolved. Okay. Where is the example? Okay. This is the example. It's the same example. Okay, let's see the plus 6 minus 6. Okay, it's the same. So in the two's complement number system, what is plus 6 with the 4-bit number system? Plus 6 is 0, 1, 1, 0, right? Because the plus 6, so MSB is 0, and then the 1, 1, 0. It's simple. Okay. Then what is minus 6? Actually, we will learn, but minus 6 is the 1, 0, 1, 0. Why? Because this is the minus 8. This is plus 2. So actually, this is the minus 6 using the two's complement number. So add. What is the result? It's a 0. 1 plus 1 is a 0, and carry is generated. 1 plus 1 plus 0 is also 0, and carry is generated. 1 plus 1 is a 0, and carry is generated. And then this is 1. But result has also 4 bits. This 1 is just removed. Okay, because also the result has 4 bits. So what is the result? The 0, 0, 0, 0 equal 0. So if we use two's complement number, and then if we just apply no more adder to the plus and minus two's complement numbers, then two's complement numbers will generate correct answers. That's why we use the two's complement division. Because if we use the same adder hardware, then also adder think that this bit is also the same number, even though this bit represents the sign bit. But if we use the two's complement number system, then the correct answer is generated. That's why we use the two's complement number. Then let's see how can we convert the plus number to the minus number. Okay, so actually I calculate like this. It's a minus 8, and then it's a plus 2, and then this is a minus 6. Then how can we convert the plus sign to the plus number to the minus number? Actually, it's different because, as I mentioned, our normal number in the real world, we use the sign and magnitude number system. But in the hardware, in the digital system, we use two's complement number system. Now, how can we convert the plus sign to the minus sign? So if we use the sign and magnitude number, then we can just change the MSB. Then it's very simple. Then how can we convert the, how can we represent the minus number? So this is the method. Invert the bits, invert the all bits and add 1. So for example, so using the 4-bit number system, plus 3 is the 0, 0, 1, 1, right? And what is the minus 3? And how can we convert the plus 3 to the minus 3? In the sign and magnitude number system, we can just add 1 in the MSB. So it's a 1011 in the sign and magnitude number system. But I said, is the system or is the system does not use sign and magnitude number system. So if we apply this method, the first we need to invert all bits of this number. So what is inversion? What is the inversion? So actually, the binary number, each bit of a binary number has only two labels. So inversion means that one is changed to the 0, and then 0 is changed to 1. That is the inversion. Okay. So if we invert every bit of this number, then this becomes the 1100. Okay. The first step is the invert all bits. Okay. And then the second step is the +1. So it's a second step, +1. So this is the 1101. And this is the -3. Why? This is -8. Okay. This is -8. This is 4. This is 1. So -8 plus 4 plus 1 equal -3. Okay. So we can convert the +3 to -3 like this. And then we can also apply the same method to the minus numbers. So which means that we can, if we apply the same method to the minus number, then we can generate the plus number. Let's see the example. So 1101 is the -3. So first step is the inversion. So this becomes the 0010, right? And then the second step is the +1, 0011. So this is the +3. Okay. So in the two's complement number system, now to perform, not to revert the sign of the number, then we can just use this method. The first step to invert the all bits of the number and then add 1. So by doing this, so we can generate the minus number, or we can change the sign of number. Okay, the two's complement number system. So just remember this. This is also important. Okay, so this is the example. And then, so this is also the example. But I already showed the example of +3 and -3. Then this is also very simple. So what is the decimal value of the two's complement number 1001? Okay, so I mentioned that in the two's complement number, the MSB is the -2 to the ups. Okay. Okay, so it's a -2 to the n-1, right? So n is the number of bits. So in this case, the n is 4, number of 1. So in this example, the 1 means the 2. Sorry about that. So this is the -2 to the 2 to the 3. So this is -8 and this is 1. So -8 plus 1 equal -7. Okay, we can calculate the we can convert the binary number of the 2's complement number to the decimal number like this. Okay, so you can just remember that, oh, this MSB, the 2's complement number system. So MSB represents the minus 2 to the power of n minus 1. Okay, just remember. Okay, then we can convert easily. We can easily convert the 2's complement number to the decimal number. Okay, or decimal number. Okay. Okay, so I already showed the example of the plus 6 to plus 6 plus 8 minus 6. Then what is the minus 2 plus 6 using the 2's complement number? What is minus 2? So actually, in order to get the minus 2 of the 2's complement number, we first need to know the plus 2, right? Then we can get the minus 2. Plus 2 is the 0, 0, 1, 0, right? And then what is the minus 2? What is minus 2? We can apply the sign conversion method we learned. Okay. It's the first step is the 1101. So invert all bits, then plus 1. So the plus 1. So it's the 1110. So you know this is the minus 2 because it's minus 8 plus 6, minus 8 plus 6, minus 8 plus 4 plus 2, right? So minus 2 is the 1110. Then plus 3 is 0011, right? What is the result? So we can just apply normal add operation to the 2's complement number system. So result is 1, 0, 0, 0. Actually 1, but this 1 is removed. So the final result becomes the 1110. Correct? Yes, it's correct. It's plus 1. So minus 2 plus 3 equals plus 1. So by applying the normal adder, we can get the correct result using the 2's complement number system. Okay, just to remember that this the system, we use the 2's complement number system, not sign and magnitude number system. So just to remember. Okay. Then how can you apply the subtraction? It's easy, right? What is your subtraction? So A minus B, that is the subtraction, right? And then actually this is the A plus minus B, right? So it means, so I said that in order to perform add operation, we require adder. So adder is a hardware unit. Then in order to implement subtractor, the subtractor is a subtraction unit, hardware unit, but we can use adder actually. Actually, in the real arithmetic operation, we can also represent the subtraction like the add operation and of negative number, right? So like add so A plus minus B like this. Okay. So why did I explain this? Because like this is the example. So how can you implement the subtraction in the hardware, hardware system, like the A minus B? Then actually we can. So this is the adder. So the adder performs the add operation using the two operand like A and B and generate the A plus B equals C. But using the same adder, we can implement the subtractor. How? So if we want to implement the a minus b, it's like the a plus a plus minus b. So which means that a is here, and then b is converted to the minus b, and then b is given to the this adder. Adder has two inputs, and then generate the c. C equal a minus b. Okay. So then how can we calculate the 3 minus 5? It's a 3 plus minus 5. So this is the 3, and this is minus 5. And if we just perform the add operation, then we can know that the result is minus 2 correctly, right? It's easy, right? So which means that using the same adder, we can implement the subtractor, okay? So in this slide, I compare the different number systems. Okay, actually, so you just so actually the hardware numbers. So hardware numbers has the different representations. So it is because hardware can only represent 0 and 1. There is no representation about the plus and minus. So actually we can use 0 for the plus, and we can use 1 for the minus sign. But think like this. Oh, this is the binary number, like the 1 0 0 0 1 1 1 0 0 0. Oh, it's a 0. Then how can you know the meaning of this number, this data? The meaning of this data can be different if we use the different number systems for this two data. Do you understand? So for example, it's the same data, so we just let's use just the 4-bit data, like 1 0 0 1. Okay, it's the same 4-bit data, but if we use the unsigned number for this data, then this data represent with the unsigned number system. Unsigned means that there is no plus or minus sign. So which means that unsigned number has included the 0 and the plus numbers. Okay, so with the unsigned number 1 0 0 1 represent it's a 1, and this is the 8, so it's 9. Okay, but if we use the sign and magnitude number system, then this is the what is this number with the sign and magnitude number system? Sign, so this is minus, then this is the magnitude, so it's minus 1. And then if we apply this complement number, then this is minus 7, right? So actually, even though the data is the same, so we can just if we just see this data, so this data is the 1 0 0 1. It's the same data, but if we apply the different number system or number representation, then this data represents the different meaning. So actually, as I mentioned, in the data system or computer, we do not use sign and magnitude number system. So we just use the unsigned or whose complement number system. So for example, so in a C programming, we can declare a data type using integer, int a, or we can declare a variable using an unsigned integer. So actually, if we declare a data type using a normal integer, so then it means that this data is represented using whose complement. And then if we declare a data type using unsigned integer, then it is just a unsigned type. So what is different? The range is different. So this is the example of the 4-bit representation. So if we use the unsigned data type, we can represent this number from 0 to 15. Okay. So if the integer has only 4 bits, then this data can represent only 0 to 15. Okay, 0 to 15. So we can, if we just assign 15 to this unsigned integer data type, then it's just 15. Okay, but the 2's complement number, then we can represent the -8 to 7 because this is a 4-bit number. So the largest negative is the 1000, it's -8. Then the largest positive is the 10111, it's 7. So actually it's a 4-bit, then we can represent -8 to 7. Then if we declare the variable a using the integer, so let us assume that the size of integer is 4-bit, and then we just assign the 15 to the variable a. Then what is this number? So 15 is the 1111, but a computer program think that this is the 2's complement number system because the just normal integer, so it's actually -1. So even though we assign 15 to this variable, actually inside of a computer thinks that this is the normal integer, and this is the -1, because we think that this data is the 2's complement number. Okay, and then we do not use the sign and magnitude, but as you can see, the sign and magnitude has a true default representation of 0. Okay, so in the slide I just compare the different number systems. Okay, so let's think about the extension of bits. So we also just differentiate the sign extension and then 0 extension, which means that we need to consider the sign bit of the number. So what is the bit extension? So I said that hardware system has limited resources. So which means that we can build the hardware using limited number of bits. But sometimes we need to extend the number of bits in our hardware. Well, sometimes we want to represent the larger number. Okay, so for example, with the 4-bit, number system here, A, and then the result is generated, and then this result is given to the another hardware unit B. But let us assume that this B handles the larger number. So we can implement this B handles the 8-bit numbers. So this is the 4-bit numbers, and then this is hardware B handles 8-bit numbers. Then with this hardware A, the result of hardware A will have 4 bits, okay? But if this result is given to the hardware B, then we need to change these 4-bit numbers into 8-bit numbers, okay? You know, it's because the hardware has the limited resources, but we can implement the hardware B using the more hardware resources like 8-bit. Then we need to increase the number of bits for number of bits of the result of this hardware A. That's why we require extension of bits. Okay. There are two different methods. It's a sign extension and then zero extension. So you may think that if we just use the COSE complement number system, we need to apply sign extension. Then if we just use the unsigned number system, then we need to apply zero extension. So it's obvious, right? So so this is the example, like the 1110, it's -2 in the COSE complement number system. Then let us assume that we want to increase the number of bits of this -2, so like the 8-bit. If we just add zeros, like then what is this number using the 8-bit number system? This number is, so this is the 4-bit number system, and then this is the 8-bit number system. And then if we just add 0, 0, 0, 0, because we need to change the number of bits of this number as the 8-bit. Okay, so what is this number? It is 862 to 14, right? It's a 14. So what is the problem? -2 is converted into the 8-bit number system, but it becomes 14 if we just add zeros. So in this case, if this number is the COSE complement number, then we need to just add ones. That is the sign extension. So sign extension means that if we just apply sign extension, we need to check the MSB. So MSB represents the sign bit of a number. Then if we just increase the number of bits, we just repeat the MSB. So 1, 1, 1, 1. So actually, this is the -2 in 8-bit number system. Okay. So if in the COSE complement number system, if the 0, 0, 1, 0 is +2, then in this case, the MSB is 0, right? Then we can just repeat the MSB to extend the number of bits. So it's the 0, 0, 1, 0, each +2. Okay. But if the number is, if a number is the unsigned number, then if the 1110 is 14. So in this case, if this number is the unsigned, then we need to just add zeros, like 0, 0, 0, 0, 1, 1, 1, 0. So it's 14. Okay. So we need to distinguish sign extension and zero extension. Just remember that we need to apply sign extension for COSE complement number and then zero extension for unsigned numbers. Okay. So so it's a sign extension, so first division 4. So as I mentioned, the 3, the 0. So the sign extension, the sign bit represents the MSB represents the sign bit. So just this MSB is repeated. Then the 0 extension, always zeros are added. Okay, that is the difference. So okay. Okay, so 41. So in the today's class, we learned about the sign two's complement number system. Actually, not to represent the negative number, we can apply the sign and magnitude or two's complement number system. But just remember that the distance of theta system we use the two's complement number system. So you need to remember how the definition of two's complement number system, which means that we need to distinguish unsigned and signed numbers in the digital hardware because the meaning is different. Even though, as I mentioned, the data can be same, but the data can be declared as the unsigned number. The same data can be declared as signed number. And then this data has different meanings by unsigned number and signed number. So we need to distinguish these different meanings. Okay. Also, when we implement the hardware that handles these binary numbers, like the signed numbers or unsigned number, we need to also consider the sign of the negative or positive sign of the number data. Okay, this is very important. Okay, so please read the chapter 1.4 of the textbook. Okay, I will stop here and then any questions? Okay, thanks for your attention. And then in the next class.